The universe didn't begin. That's not a spiritual claim. That's not a philosophical argument. That's what the physics actually says when you follow the equations all the way to the edge. You've been told there was a beginning, a moment, a cosmic explosion that created everything from nothing. Every documentary, every textbook, every Carl Sagan voiceover says the same thing. The Big Bang happened 13.8 billion years ago. Before that, nothing. The universe didn't exist. But here's what they never tell you. The Big Bang model, the actual equations, the real mathematics breaks down completely at the very moment it's supposed to explain. The physics doesn't describe a beginning. It describes a boundary, a wall where our understanding stops. And beyond that wall, we have no idea. I'm Leonard Susskind. I've spent 50 years working with the equations of cosmology, quantum mechanics, and string theory. And what I've come to understand about the Big Bang is something that most science communicators don't want to say out loud. We've been telling the public a story, a clean, satisfying story. And the real picture is far stranger, far more unsettling, and in some ways far more beautiful than anything we've described. The Big Bang, as most people understand it, never happened. Let me show you why. And I promise by the end of this, the universe will feel completely different to you. Start with what the model actually predicts. General relativity, Einstein's theory of gravity, one of the most tested theories in the history of science, describes how space-time curves in response to energy and matter. When you run this theory backward in time, following the expansion of the universe in reverse, you find that everything gets compressed. The universe gets smaller, denser, hotter. And at a certain point, roughly 13.8 billion years ago, all the matter and energy in the observable universe was compressed into a region smaller than an atom. That's already strange enough. But here's the part the textbooks gloss over. When you compress everything into that smaller region, the density becomes infinite. The temperature becomes infinite. The curvature of space-time becomes infinite. In mathematics, when a quantity becomes infinite, we call that a singularity. And a singularity doesn't describe a physical event. It describes a place where your theory stops working. A singularity is not a beginning. It's a failure. It's the equations throwing up their hands and saying, I can't tell you what happens here. The physics breaks down. The laws of nature as we understand them cease to apply. Every prediction the theory makes becomes meaningless. Think about what that means. The most powerful theory of space and time that physics has ever produced, the theory that predicted black holes, gravitational waves, the bending of light around stars, all confirmed, all verified to extraordinary precision, this theory cannot describe the first moment of the universe. Not because we haven't thought hard enough, not because we lack computing power, but because the mathematics itself becomes undefined. So when someone says the Big Bang happened at time zero, they're describing something the theory literally cannot say anything about. Now you might think, okay, but the universe is clearly expanding. We can measure it. Edwin Hubble measured it in 1929 galaxies, moving away from us in every direction. The further they are, the faster they recede. The cosmic microwave background radiation, the faint afterglow of a hot, dense early universe, is measured to extraordinary precision by satellites. The abundances of hydrogen, helium, lithium in the universe match the predictions of Big Bang nucleosynthesis perfectly. The evidence for an early hot dense state is overwhelming. I'm not arguing with any of that. What I'm saying is something more subtle. The evidence tells us the universe was once in an extremely hot, extremely dense state. It tells us the universe has been expanding and cooling for billions of years. It does not tell us there was a moment of creation. It does not tell us what happened at the singularity. It does not tell us what, if anything, came before. The word before is already doing suspicious work in that sentence. Because here's another thing the Big Bang model implies, something even stranger than the singularity itself. Time, as we understand it, may not have existed before a certain point. Stephen Hawking and Jim Hartle proposed what's called the no-boundary proposal. The idea that asking what happened before the Big Bang is like asking what's south of the South Pole. The question sounds sensible, but it's grammatically correct and physically meaningless. In this picture, time itself emerged with the universe. There is no before, because before requires time, and time didn't exist yet. Does that solve the problem? No. It relocates it, because now you have to ask, what does it mean for time to emerge? What does it mean for something to exist before time exists? The word before is a temporal concept. Use it to describe the absence of time, and you've tangled yourself in a conceptual knot that physics hasn't cut through. This is where I think the popular science narrative goes wrong. It takes the genuine, hard-won observational evidence for an early, hot, dense universe and wraps it in a creation story, a beginning, a moment when everything started. And that story feels satisfying. It has a shape we understand: beginning, middle, and presumably end. But the universe doesn't owe us a satisfying narrative. Let me go deeper, because in the last few decades, theoretical physics has developed models of what might lie beyond or beneath the Big Bang singularity. And these models paint a picture that is almost impossible to describe in ordinary language. The first is eternal inflation. The idea of inflation was proposed by Alan Guth in 1980. It solves several puzzles about the Big Bang: why the universe looks the same in every direction, why space appears to be almost perfectly flat, why the cosmic microwave background has the pattern it does. The solution is elegant. In the very early universe, space underwent a period of exponential expansion, doubling in size over and over again in an extraordinarily short time. Quantum fluctuations during inflation were stretched to cosmic scales, eventually seeding the galaxies we see today. Inflation works. The predictions match the observations. But here's what Guth and others discovered almost immediately after the inflationary model was developed. Inflation, once started, doesn't stop. In most regions of space, inflation ends. The exponential expansion transitions to the more familiar, slower expansion we observe today. But in other regions, regions that are expanding so fast they're beyond our ability to observe or affect inflation, continues forever. In this picture, our observable universe is one bubble among an infinite number of bubbles. Each bubble forms when inflation ends in that region. Each one begins its own story of galaxies and stars and perhaps life. But the inflationary sea goes on forever, generating bubble after bubble, universe after universe, without beginning and without end. There is no starting point, no moment of creation, no first bubble, just an infinite ocean of quantum space-time, frothing with universes. This is what the mathematics of inflation leads to when you follow it honestly. Not a single beginning, an endless, beginningless multiverse. Now, I want to be careful here. Eternal inflation is not established fact. It's a theoretical framework with good supporting evidence and serious theoretical backing. But it makes predictions that are, in principle, untestable from within our bubble. And physics requires testability. Still, the logic is hard to escape. If inflation happened at all, and the evidence strongly suggests it did, then eternal inflation is almost certainly the result. It's not an additional assumption. It follows from the same equations. And if eternal inflation is real, then our Big Bang is not the beginning of everything. It's one local event in a structure with no beginning. But there's another possibility, one that goes even deeper. Quantum gravity, general relativity, and quantum mechanics are the two pillars of modern physics. Relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Both are extraordinarily successful. Both have been tested to extraordinary precision. They are also fundamentally incompatible with each other. When you try to combine them, when you try to describe gravity using the mathematics of quantum mechanics, you get answers that don't make sense. Infinities appear where they shouldn't. The equations break down. This is the problem of quantum gravity, one of the deepest unsolved problems in all of physics. The reason this matters for the Big Bang is this. The singularity that general relativity predicts at the beginning of the universe is precisely the kind of situation where quantum gravity becomes essential. The densities are so high, the scale so small, that quantum effects on space-time itself become significant. We don't have a complete theory of quantum gravity. String theory is the most developed candidate. Loop quantum gravity is another. There are others. But here's what almost every approach to quantum gravity suggests. When you properly account for quantum effects, the singularity disappears. In loop quantum cosmology, for example, the Big Bang singularity is replaced by a big bounce. The universe doesn't begin at a point. It contracts from a previous state, reaches a minimum size, still unimaginably small, but finite, and then expands outward into the universe we observe. Our Big Bang is the bounce, the emergence from a previous contracting universe. And what was that previous universe? It too expanded, cooled, contracted, and bounced. And before that, another universe? Bouncing, expanding, contracting, bouncing again? In some versions of this picture, the series of bounces extends infinitely into the past. No beginning, just an endless chain of cosmic cycles. Other versions suggest the bouncing eventually reaches a true beginning, but a beginning that is finite and well-defined, not a singularity, a moment that quantum gravity can actually describe. The honest answer is, we don't know which picture is correct. We don't have the experimental tools to probe the physics at the Planck scale, the scale at which quantum gravity becomes relevant. The energies involved are roughly 15 orders of magnitude beyond what the Large Hadron Collider can reach. I want to tell you something personal here, because I've spent a significant part of my career working on string theory. And string theory, for all its controversy, does something remarkable when applied to cosmology. It suggests that the number of possible universes, each with different physical constants and different laws, is not just large, it's incomprehensibly large. Something like 10 to the power of 500. Most people hear that and think, what does that have to do with anything? But here's why it matters for the Big Bang. If there are that many possible universes, and if eternal inflation is continually generating new regions of space-time, then what we call the Big Bang might be nothing more than the local initialization of one particular set of physical parameters. Our laws of physics, the speed of light, the strength of gravity, the mass of the electron, these are not fundamental truths about all existence. They're one roll of an unimaginably large cosmic dice. And there's a number that makes this concrete. The cosmological constant, the energy of empty space that drives the acceleration of the universe. When physicists calculate what this number should be from quantum field theory, the answer is roughly 10 to the power of 120 times larger than what we actually observe. That is the largest discrepancy between theory and measurement in the history of science. Why is it so small? We don't know. Unless, and this is the argument many physicists find troubling, the value isn't small because of some deep principle. It's small because in a multiverse of universes with every possible value, we inevitably find ourselves in one where the value allows us to exist. A larger cosmological constant would have torn the universe apart before any galaxy could form. No stars, no planets, no us. We observe a life-permitting universe not because it was designed, but because we couldn't be asking the question in any other kind. That might feel unsatisfying. Good. It should. The universe is not obligated to satisfy us. So where does that leave us? Here's what I believe. After 50 years of thinking about these questions, the Big Bang, understood as the beginning of time, the moment of creation, the origin point of everything, that version of the Big Bang is almost certainly wrong. Not wrong in the observational sense. The universe really was hot and dense. The universe really has been expanding, but wrong in the philosophical sense. Wrong as a story about beginnings. What we call the Big Bang is better understood as a transition, a phase change, a moment when conditions changed so dramatically that everything we know about physics stopped applying. What was on the other side of that transition, whether it was a previous universe, an inflationary sea, a quantum space-time foam, or something we haven't imagined yet we genuinely do not know? And this uncertainty is not a failure of science, it's a frontier. Let me tell you what I find most extraordinary about this. The fact that we can even ask these questions, that we can look at the light left over from the first moments of the observable universe, that we can measure the afterglow of the early universe's heat to 6 decimal places, that we can infer conditions from 13.8 billion years ago from observations made on a small rocky planet orbiting an unremarkable star. The fact that the universe apparently contains beings capable of looking back toward their own origin and questioning the story they've been told, that's not obvious. That's astonishing. But here's what I want to leave you with. The story you've been told about the Big Bang is incomplete, not wrong in every detail. Incomplete in the most profound way possible. It stops exactly where the questions get interesting. What was there before the singularity? We don't know. What caused the universe to exist rather than not exist? We don't know. Is our universe one of many? We don't know. Does time have a beginning? We don't know. And here's why that matters. In science, the questions we can't answer tell us where the real discoveries are waiting. Every open question is a door. The singularity isn't the end of the story. It's the place where the next story starts. The universe didn't begin 13.8 billion years ago. Something happened then, something extraordinary. But whether that something was a beginning or a transition or an emergence from something deeper, that is the question theoretical physics is working toward right now. And the answer, when it comes, is going to change everything you think you know about existence itself. We are standing at the edge of what we know. And the edge is right where the Big Bang was supposed to be. Think about that. Really think about it. The universe handed us a mystery wrapped inside its own origin, and we're only just beginning to unwrap it. After 50 years of listening to what physics says, the one thing I'm certain of is this: the universe is stranger than the story we tell about it. Always, without exception. And that is not a reason for despair. That is the whole point.